of PEPM' 2026. It's my pleasure to introduce our invited speaker, Nicolas Wu. Nicolas Wu is a professor of computer science at Imperial College London, where he leads the functional programming group. His research interests including algebraic effects, effect handlers, modular language design, and the use of functional programming techniques to structure and reason about complex systems. All right, Nick, the stage is yours.
Thank you very much. Okay, so a big disclaimer. There are a few disclaimers to make. One is that this is not the first time I've done this talk. So if you already went to the Haskell Symposium keynote a few years ago, when Ning Ning did the keynote as well, I gave basically basically the same talk as this, and she invited me to basically give it again. So here we go for part 2. So this is why we're just revisiting the evolution effects. And the second disclaimer is that this is largely a talk about history, and I'm wondering if we can turn down the speaker a bit. Is that possible? Because I feel like I'm going to explode if I carry on. Thank you, that's great. This is largely a history lesson, and the problem with history is that you can never get it right no matter how hard you try, because there's always something that you'll forget and you'll always have a biased view. And I'm definitely guilty of both of those things. So I'll do my best to try and be slightly objective, but I will certainly get all sorts of things wrong. And if you like to heckle, I don't mind you heckling during the audience, during the talk, and you can just tell me that I've got something wrong or tell me something I didn't know before. Certainly this talk has been improved a little bit since last time due to the heckling. Okay, so this talk is in 4 parts. I'm going to be talking about the history of evolution effects, starting with something like the history of programming languages, moving into monads, then effect handlers, and then higher order effects. Okay, so it's very peaked. And caveat, there's just too much history to cover everything. I'm not really going to make a good job of it. But let me just start with some basics. There's this common divide between functional programming and imperative programming, and it's been here for a very long time. It's been here essentially since the beginning. We've got Alonzo Church sitting in the functional camp, teaching us all about the lambda calculus, and then we've got his what became PhD student, Alan Turing, thinking about imperative programming. And so you've got, you know, the good guys versus the bad guys from the beginning. He's saying, you know, the right way to do programming is to use lambda abstractions. This is how we should understand programming languages. Whereas Turing says, no, no, it's machines and it's all about assignments. So this is how we should be thinking about what computation is. Fine. So this is where the story starts. So let's think about programming languages and maybe where they came from. So this is a history lesson after all. I'm at Imperial College London, so I feel like I have to start in London. In London in 1666. London is on fire. It's the Great Fire of London, started by some small bakery in some obscure alleyway, which basically took over the entire country. But 1666 is important for another reason. It's also the year when Leibniz completed his dissertation, The Art of Combinatorics. And so this is a snapshot of his actual thesis. And it's an interesting piece of work. It includes all sorts of stuff, including a proof of the existence of God from some hypothesis about and axioms about motion. It's an alphabet of human thought that he wants to build, the Alphabetum Cogitunium Humanium. My pronunciation's wrong. And the idea is that he thinks that all human concepts can be put together into some kind of common language so that we could start reasoning about things, so that when we're arguing about something, we can, rather than just arguing with random words, we can maybe write them down and then start calculating our way through an argument to see who's right. So that's kind of his goal. And so he also has some interesting writings. He says something like, when trying to get from England to Holland, I was detained for some time in the Thames by adverse winds. During that time, knowing not what to do and having nobody in the ship except sailors, I meditated on things and especially thought about my old design of a rational language. Just think of that scene. So he's on the Thames with nothing but sailors, and so he starts thinking, right? And so if we can have such, as I imagine, we could reason about metaphysics and morality just like we do about geometry and analysis. So he's really thinking about logic as a language. And he's writing this to someone called Galois, but not the one you're thinking of. So was he a programming language designer is the question. Was he thinking about disassembling and composing languages from smaller parts? Let's fast forward a little bit to a different keynote talk, but this one to a much more prestigious venue, sorry, PEPM, the Congress of German Scientists and Physicians in 1872. Emile Dubois-Reymond says, Basically, at the end of a long talk, which was about how there are limitations to what science can know, and that there are certain big questions that we'll never get around to answering, he says, ignoramus et ignoramibus. We do not know, and we shall not know the answers to these questions. So there are just simple limitations, and tough luck scientists, but we'll be out of a job if we try to answer everything. Fine. And that really annoys David Hilbert. David Hilbert, a few years later at the same conference, also a keynote speaker, responds to this message saying, wir müssen wissen, wir werden wissen. We must know, we shall know. So he's kind of very defiant about this. And so he decides that, okay, actually, I think we can decide with certainty the true answers to all scientific questions, or at least all mathematical questions. And so he devises in 1928 with Ackermann a whole bunch of interesting questions, but in part, one of the questions that he has is the Entscheidungsproblem, the decision problem, basically asking us, given a particular input statement in first order predicate calculus, is there an algorithm that answers either yes or no if the statement is provable? And it seems perfectly reasonable, right? Because we're thinking of a mathematical language. We know that mathematics is supposed to hold something to do with the truth, and presumably we can always calculate what the truth is, right? That's kind of the goal, the question. And I think at the time it was basically understood that the answer to this would be yes, right? People thought there's no question that mathematics can't resolve all of its own questions. But I think everyone in this room probably knows how this goes. But partly we've got Gödel in 1931 saying that any reasonable system of logic has true statements that cannot be proven within that statement. So that's already quite a worrying fact. And so we can always think about maybe extending the logic to have more predicates or something like this, or doing some more meta logic. But eventually we'll run out of meta, and we'll know that we can't prove everything within our language. Fine. And if it holds true, then perhaps, but maybe there is an algorithm that can prove that statements are one or the other at least. In 36, we get two answers to that question, again by Church and Turing, and they basically say no, there's no such possible answer. So we have the halting problem getting in the way. There are true limitations to what we can logically get to. Okay, and to this PL community, I think you probably roughly know where that goes. Of course, Turing was involved shortly after in the development of the first computer, and partly with the help of von Neumann and a whole bunch of other people. And I think the history here is quite difficult to get right and murky, so I will make no attempt to get it right, and I'll just go for something that's wrong. There was the EDVAC computer in 1949. There's also the ENISAC. Or the EDSAC, sorry, and I think the Americans and the British fight over who got there first, but it was definitely the British. And so there we have it. We have machines have made their way into our world that can compute. And of course, the first thing that happens is that we start thinking about a programming language for these machines. So rather than working on, literal punch cards like this, we want, well, actually, this is a punch card that is exactly this code. But rather than just working with wires, we want to work in a programming language where punch cards like this translate exactly to things like this, right? So we think we've got it hard working in the terminal when we're not using VS Code, perhaps. Imagine if you really had, a hard limit of 80 characters set by a piece of paper, and that you really have to sort of punch in the exact symbols that correspond here. So the way to read these is literally, this is a single line of code. And so you've got, here is each of the columns that correspond to where the character is. And going down the page is going to be the bit sequence that you require to make that particular bit character for that particular line. So a stack of punch cards. Each punch card is one line. A stack just corresponds to your program, et cetera, et cetera. So there are some people, when I give this talk, they're like, oh yeah, I remember punch cards, and I've got a few right here. But for most of us in this room, this is a forgotten thing. We have no idea where we've come from. Okay. But what did Backus say about this? He invented the language called Fortran, and he said in this really nice article in Think, which is one of IBM's notices, he said, much of my work has come from being lazy. I didn't like writing programs, and so when I was working on the IBM 701, writing programs for computing missile trajectories, I started work on a programming system to make it easier to write programs. Most people think Fortran's main contribution was to enable the programmer to write programs in algebraic formulas instead of machine language, but it isn't. What Fortran did primarily was to mechanize the organization of loops. So back from the beginning, it's actually interesting that it's control flow that's the thing that was difficult, or control flow was the thing that was in his mind in terms of trying to come up with a programming language. And that'll become obviously relevant in a talk about effects. Fast forward just a tiny bit, or sort of in a round era actually, we've got Lisp, so a second contender for being the first proper programming language. And so this is McCarthy taking a very different take on what a programming language should do, where we saw Backus in the previous slide thinking more about how we can work with the machine and talk about machine language and make that process easier. McCarthy's coming from the other perspective. What can we do with the lambda calculus and how can we enact that in a machine? And so these are the two views that we got right from the beginning, the imperative versus the functional, kind of attacking the same problem all over again. And we can see here that he really is writing the lambda calculus in his papers in 58. And he's saying things like, okay, here's what a conditional expression should look like. We should handle each of the, in a case expression, we should handle each of the cases with saying if P is true, then if P1 is true, then do E1 and so on and so on. So this is starting to look something like we'd have in effect systems today even. He basically wants to say something like we should really have continuation. So continuation, if the thing is false, we should do something. If a continuation is true, we should do something else. So he's thinking about things in terms of continuation style, which will become relevant later on. Another thing that he has in this really early paper is the map function, which as functional programmers is one of the first things that we learn. So if you have some list x and some function f, then if the list is nil, then you do the nil thing, and if it's otherwise, you do the cons thing, you put them together and so on. Interesting note is that I think car and cudder are the names of head and tail respectively. So I find it quite amusing that they call it car and cudder in the underlying documents rather than what we might call head and tail, in the sense that what on earth does car and cudder even mean is probably the first question some of you are asking. And so one is the address part of a word and the other is the decrement part of a word. And obviously they correspond to the head and tail of a list, right? And I think the perspective here is that they're really thinking about what's going on in the machine. And even in this paper, which talks about lambda abstractions, they can't get away from the underlying concrete representation of certain data structures. And they're not fully making that step to thinking about things in terms of those data structures themselves. And I think that's quite curious as well. So, right. And also in 62, McCarthy comes up, as far as I can tell, with the first use of the word abstract syntax. So that's where we should go to understand this idea of having abstraction. So nice that he might have moved away from car and cudder, I'm not sure. Let's fast forward just a tiny bit further into Algol 58, where a number of people who established a lot of PL as we know it today, came together and decided to write a common language that they could use for writing papers in, basically. I think they were tired of reading papers about programming languages in all sorts of different languages, and they thought, I know, let's come up with a language that we can use to communicate in the CACM. Obviously, we didn't listen to that at all. If you look now in POPL, you'll see we never write, I think probably almost no two papers write in the same language. But what they did do is they laid a foundation for what kind of programming languages features we might like. And so it's nice to see that Backus and McCarthy, these two sort of fathers of the first imperative language and the first functional language, came together and created this thing, right? What was special about Algol? Well, it had things like iteration and also recursion. It had this idea of distinct assignment versus equality, so that we can actually tell the difference between these things. There was the idea of code blocks, and lexical scope was new to this language. Nested procedures and procedure passing was important too. BNF was invented, so Peter Noir and Backus was the other author of that. They invented what we now use to express our grammars in. And the distinction between call by value and call by name was invented for this language. So all sorts of interesting things came out of the development of this important language that's really seminal to us all. And Tony Hoare at the time said, it's a language that's so far ahead of its time that it was not only an improvement on its predecessors, but also on nearly all its successors. If you look at the state of some programming languages today, then you might agree with him. Right. Let's move on a little bit into 1965. So I think the conclusion that I have is the first iteration of Algol feels exceptionally imperative in nature. Peter Landin, I think, takes slight issue with this and starts thinking about whether or not it's possible to think of algol in this sort of functional way. And actually, he's doing this because he wants to give a semantics to algol and understand that from a computational perspective, from a lambda perspective. And so he writes this paper in '64, The Mechanical Evaluation of Expressions, where he shows how you can translate some algol code into the corresponding, what he calls applicative expressions, which are just expressions that you can apply to each other. So literally just lambda abstraction and lambda application are the tools that we have. Some distinction between lets and wheres, but it's interesting from a Haskell perspective, we're always allowing both lets and wheres in our languages. And he invents what we call the SECD machine, which is the first abstract machine for evaluating lambda expressions. So he shows us the connection between Church's calculus and machines themselves. So the SECD machine allows you to actually take a lambda expression and fully evaluate it right the way down. And so we see this really clean connection between the two in this paper. And so I think this makes its way into the standard understanding of algol in '65, and he shows that basically the two languages are the same with all the different concepts corresponding quite naturally. A little bit later on, Landon gets a little bit more extreme with his views and decides that what we need is a new programming language called ISWIM, which means if you see what I mean. I think it was the fashion at the time to name languages after obscure acronyms, and I think he was making fun of that. So in 1966, he writes this famous paper, which I think I'd recommend to everybody in this room to read, just because it's quite fun to see how research has changed over the years. This was definitely a seminal paper, but when you read it, you see that it's just written in a completely different, much more flourished style than we would today. And in this paper, he basically thinks about doing church without lambda is the subtitle that he gives to this paper. So he's thinking, okay, so the lambda calculus was a really nice language to give the semantics of things, and we were able to give the semantics of algol using that. Great. But what if we were to start from the ground up and think of a language where we're not writing lambdas, but we can program in that style? And so he's thinking about basically what I would say is a real predecessor to Haskell. If you start looking at ISWIM, you'll see huge similarities between that and the way Haskell ended up being, and that's no coincidence. So he wants us to be able to write programs like this and where you have some kind of expression with a where clause, just sort of saying how things are and plugging it all in. What's interesting about papers in these days isn't just that the content of the paper is written and expressed in a different way than we would today. They also have something fascinating, which is at the end of the published paper, you get a transcript of the questions that were asked at the talk. And so you can see who asked what and how it was responded to. And I think that's really, again, an insight that we no longer have. And so Peter Noir says, oh, well, regarding indentation, since ISWIM was an indentation-sensitive language, in many ways I'm in sympathy with this, but you would regret it because of the kind of rearrangement of manuscripts done in printing, which tickles me because, as you all know, when we're using LaTeX and we're trying to get that camera-ready version with just the right number of pages, it's an absolute pain whether it's indentation sensitive or not, right? But yeah, so these problems have not changed over the years. So this is a language like Haskell that has pattern matching, it has where clauses, it has garbage collection, and it's indentation sensitive. But it's also equipped with equivalences for reasoning. So he wants us to be able to write in our programs equivalences between expressions and hope that your language will be able to resolve those equivalences and say that these two terms must be equal under this in this language. So for instance, he thinks that the languages should always have these rules. So sub-expressions should be congruent. We should have multiple ways of defining the same constructs. So let statements and where statements shouldn't be so different. He thinks that we should have built-in expressions, so true and false resolving as an if then else statement should be doing something like this. And also, and interestingly for us, he wants there to be user-definable DSLs, so domain-specific languages that the user can write, and then use those languages in the code that they're writing itself. And within those languages, you would be able to write some equalities on the expressions that are there as well. And so that's what we have here. So he says the problem orientation of ISWIM can be characterized by additional axioms. So he's thinking about additional equalities between operations here. In the simplest case, such an axiom is an ISWIM definition. The resulting modification is called a definitional extension of an original system. Okay, and when I said the language in these papers is a bit hard for us to decipher today, it's basically stuff like this right the way through, right? So you have to really read it quite carefully and get into their mind and work out what's happening. Okay. I want to kind of move on a little bit to the idea of structured programming because that was really relevant to ISWIM. ISWIM was really good for reasoning and doing structured programming, and I think that's probably one of the biggest gifts that it gave us. And structured programming was, let's say, advertised by Birstall in '68, where he's viewing the idea that we should have code and where reasoning about that code should follow the structure of that code. So he's tying together the idea of data structure and induction should really be tied in together. And so to prove the correctness of your favorite algorithm means to follow the structure of that algorithm and to make equalities about that and to make statements about that. So he implements really early versions in '68 of the concat, and this is the fold right function, which collapses the list. And then he writes about a function for sorting via flattening trees. And so if you look at this code, you'll see it looks fairly functional. It looks like Haskell again, but this is an ISWIM, of course. And what's interesting about it isn't so much that he has an algorithm that does tree flattening, it's that he actually does a proof of its correctness by induction over the structure of that tree as well. So we're seeing all sorts of nice techniques that we'd like to mechanize today, but implemented by hand at that time in a language that didn't ever really exist at the time. So there was no implementation of ISWIM in this period. That came much, much later. It was really a pen and paper language in this moment. Okay, and the idea of this really takes off and then was popularized by others. So Dijkstra, Hoare, and Dahl wrote this really nice paper called Structured Programming, where it goes through lots of examples of why you might want to structure your code rather than just using a control structure. You can actually use data structure to manipulate things. And again, that's something we would teach all our undergraduates today. And Hoare writes that there are certain close analogies between the methods used for structuring data and the methods for structuring a program which processes that data. So again, these ideas of making program and data be the same kind of thing is emerging at this stage. But we're not quite done yet, because another big idea that came out in this Next 700 Programming Languages paper was, I think, the foundations of denotational programming, or denotational semantics. So he says something like, the thing an expression denotes its value depends only on the values of its sub-expressions, not on other properties of them. So that's in '66, and in '71 we get Scott and Strachey showing us how to unpack this into mathematical formulas. So we've got an expression, and we give that a denotational semantics when the meaning of the expression comes about as the meaning of its parts. So we've got this V here, and we're looking at the parts to combine them. So that paper was really foundational in the sense that it gave us this idea of having what I might start considering a higher order language with interesting pattern matching, with lambdas at the heart of it, and yet that should be quite easy to use, that's ready for structural induction, and also giving us denotational semantics. So it's an important paper for lots of good reasons. Okay, so back to our initial slide, we've got functional versus imperative. Are they really at war? Well, Peter Landon, I think his take would have been slightly different. He would have said, actually, there are all sorts of different words that we might use to describe what we want. Maybe we're saying things like procedural, non-procedural, algorithmic, heuristic, imperative, declarative, functional, descriptive. But we probably should have a different classification of the kinds of languages that we want. So here's a new word that he wanted to invent to describe the good languages. And he thinks that we should call them denotative. So the denotative languages are the kind of that part of the imperative world, that part of the functional world that we think is sensible, right? Okay, so maybe we've got some kind of, mystical, right? Perhaps there's a means of working with pure functions and side effects in synergy. And this would require a denotative means of expressing side effects that supports reasoning. So we should put denotation at the heart of our languages. We should try to understand what the code means. And if we can do that, then maybe it doesn't really matter too much whether we're doing imperative or functional programming. Okay. So now on to monads. We all perhaps have heard the folklore that monads are burritos. If you haven't, well, welcome to the world of monads. Monads or burritos was a kind of a joke, I think, that Brent Yorgi wrote in a blog post where he was just talking about the monad tutorial fallacy. This was a kind of interesting time on the internet when if somebody learned a new idea, then they would write about it in their blog. And so there were lots and lots of different analogies about monads and what they really were. And so to kind of talk about this aspect, Brent jokingly wrote, monads are like burritos, and then I think it took off a bit too well. So that's where that idea comes from. But because we're doing history, I thought I would take us right the way back. So this is South Africa in 71,000 BC. And I kid you not, this is actually a picture of a rock that exists from 71,000 BC, we believe. And archaeologists had to look at this thing very carefully. You can see these ochre red lines on it. And they've gone so far actually as to write papers about this. So it's an abstract drawing from 73,000-year-old levels in this particular cave. And they've analyzed this rock very, very carefully. And you can see these red lines where the markings of somebody they've very carefully written something here. And the question is, what is the message that they're trying to get across? Now, to me, it's absolutely obvious. You look at this and you realize that mankind's been striving for Haskell for a very long time. So that's not actually the history of Haskell. The history of Haskell was kind of spotted nicely in this paper, not in South Africa, 71,000 BC. And so here's a nice picture with the people who got together and wrote the first Haskell report. And you can read all about this in this nice report. I would recommend you read that too. And I think their take is that Haskell brought lots of different things. One of the important features that it brought was the class system. But another feature that it did bring, I suppose, was monads. I say I suppose because it wasn't in the original design of Haskell. Monads came not as an afterthought, but as a kind of a solution to a problem, which is how do we deal with I/O? And the initial versions of dealing with I/O were really just about having a single pure function that took in a string and output a string, and the input string was lazy, and you could produce your output and then keep on consuming some more of the input as you go to react to the world. And then, of course, monads became the solution that they fell on and was shipped in the first version. So I thought it'd be good to just go into the history of monads a little bit and see where that came from. So if you end up being interested in category theory, then one of the rituals that you'll probably go through is picking up a copy of categories for the working mathematician and probably being a bit confused by what's in there. But it is a good place to look at where things came from. And right near the beginning, MacLean says that monads came as a construction in passing in another paper that he wrote. Here it is written in 1956. And it's fitting that it's in French because that's what he wrote in this language. And here it is saying something about the utilization of two categories, K and L, with a functor T, et cetera, et cetera. But these four lines are what he's referring to in his book, saying this is where monads were first introduced in passing, right? That's what he thinks a monad is in this place. So Godeman does a slightly more, a slightly bigger exposition of this, again in French, where he talked about monads, and it started to become a bit more clear. In the paper, you can think of K as being return, P as being join, and you've got an equation here at least that looks like the monad laws if you know what they are. But basically, this is the first time when we really start seeing monads crystallizing in the way we would understand them today. And so for years, these things didn't really have a name. And I don't know if that's actually better or worse than today, because if you tell an undergraduate that we're going to learn about monads, suddenly they look terrified. And if you tell them we're going to learn about stuff, it's OK. So they called it the standard construction, or the fundamental construction, or just triples. But what about the word monad? Where did that come from? Why do we have it? So that was due to someone called Jean Benabou in '67, and he's writing about bicategories. And he wants to play on the word monoid, but actually he's not thinking about that so much. He's also thinking about monads as opposed to polyads. So our choice of monad comes from an example of definition 5.5. 5.5 is about polyads, and from polyads he basically thinks about not multiple arguments in these things, but one argument in these things. So it's a monad rather than a polyad. So that's the idea, really. So it's not so much about monoid, although it does bring that in. It's in contrast to polyads, which is not a concept that we use so much now. Okay, so that's where monads came from, and I think understanding where category theory injected itself into computer science started out. So as far as I can tell, the categorical semantics were basically explored by IBM as a kind of an initial idea. We've got Eilenberg and Wright writing this paper about automata in general algebra. They're talking about universal algebras for automata using Louvre theories. For those of you who know about effect systems, Louvre theories are a way of talking about operations and equations between those operations. And so it's really nice that in one of the first uses of computer science with category theory, we have something that harks right to what we'd think of now. Let's see. It's interesting as well that in this paper, for them, it's saying basically this paper contains nothing new except perhaps for a new point of view. I think that's such a throwaway remark. That's having new perspectives on old material actually is super useful, and we've seen that time and again. So I don't think I would phrase it quite like this. I think it was actually a really important thing that they did. In '71, Algot started talking about algebraic theories for program schemes and wrote about monadic computation and iterative algebraic theories. So that was in '73. So he's thinking about iteration, thinking about how that can be done. And he's connecting Louvre theories with the way we'd study Turing machines. So that's where we have some interesting work to start with. Rewind a little bit to 1970, so just about 3 years or so before, we have Mac Lane, and he was suggesting to Gauguin that maybe he should apply for a research fellowship at IBM. And so, you've got the founder of category theory saying, why don't you apply this stuff in IBM? That would be a good idea. And so Joseph Gauguin goes ahead and forms what was known as the ADJ group, or the adjunction group, or which they were trying to do something like the Nicolas Bourbaki program, which was a rewrite of not foundational mathematics in the Bourbaki style, but rather the foundations of category theory the foundations of computer science using category theory. So he and Thatcher, Wagner and Wright get together and they write this paper called A Junction Between Computer Science and Category Theory, Part 1. And I think they had something like 4 parts planned out where they would go through all these different constructions and show why category theory is the foundation of computer science. The joke here is that an adjunction is a categorical construction that's quite important, and so they're writing a junction between and I. Okay, so they like the puns from the beginning, and that's why they call themselves the ADJ group, because they're the adjunction group. Okay, so then there was part 2 of this, which shows some more examples of these ideas, but it was a hugely successful project, although in the end I think they didn't have time for any more of the parts. They only got as far as part 2 and then ended. But they did talk about things like initial algebra semantics and continuous algebras. Initial algebra semantics is the way that we would give a semantics to things like a fold over a list or a fold over some larger data structure. It's the way that we would give proofs in a language like Rock or Agda. It's all about an initial algebra semantics insofar as induction is concerned. But yeah, they never made it past report 1 or 2. And I forget why this slide is here. So we've got an algebraic theory of recursive programs. Okay, so they use, that's right, so Burstall and Thatcher used monads to explain stateful programming and how it was related. And so they have this diagram here where you've got the familiar semicolon in the middle, and they're saying, okay, you should be using monads to think about stateful programming. So this is in '75, quite a long time before we think of monads and stateful stuff today. So what about monads and the lambda calculus? Where do those connections come in? So we've got Dana Scott, who thought about denotational semantics, and he writes this paper in 1980 relating theories of the lambda calculus, and something he says is that we want a pure theory of functions, and that is category theory. So he says, everyone agrees that the lambda calculus is a theory of functions, but we must ask what kind of a theory? And also, have we got the best theory? Personally, I think we should also inquire, how does it relate to other theories? I certainly find many discussions far too silent on this last issue. And then he goes on to say, what then is a pure theory of functions? The answer, category theory. So he thinks that if you're thinking about functions, then you really should be thinking about the foundations of that, and category theory is the right lens to view those. Fine. In 1980, we have Eugenio Moggi, and he takes this view and uses monads to give a semantics of computations. And so this is the 88 paper where he explicitly thinks about the lambda calculus and monads. He takes the categorical semantics and he shows various monads and why they're relevant to programming. Right, so he thinks about side effects and state, side effects with state and exceptions in monads, and he makes that crystal clear in 91. There he models other notions of computation. So we've got partiality, non-determinism, side effects, exceptions, continuations, input and output. All of these different examples were made in that paper. So the story for effects is obviously related to that, but in the way we'd understand it today, I'd like to take us back to 85 when Phil Wadler is thinking about how we can replace failure with a list of successes. So how can we record for a program to fail? And he's thinking about lists and laziness and combining these ideas together. And so he's thinking about exception handling, but in a kind of a listy way. So that's what he does in 85. And when I read this paper, I was quite excited because I'm at Imperial College and ICL, and he says, part of this research was performed while on research fellowship supported by ICL. I thought, wow, Imperial were at the heart of this stuff as well. That's really interesting. And then I saw Phil at, I think, ICFP, and I said, Phil, I didn't know that you were at Imperial. And he said, I didn't know either. Because ICL, of course, doesn't stand for Imperial College London. It's some completely other company, a different company. So there we go. It does not mean Imperial, it's something else. Okay. In 1990, although it was first submitted in 88, Spivey looked at the functional theory of exceptions. So at the time in 85, Phil Wadler was thinking about exceptions, thoughts about them in terms of lists. Spivey also took a look at this, and I chatted to him about this, and I said, had you read Phil's paper? He said he hadn't. What he was doing at the time was reading MacLane actual, and then when he was reading MacLane, he got to the monads, and he thought, this is what we should be using for composing together exceptions. And so he introduces the word maybe, which we use today for programming with exceptions, and he explicitly uses just and nothing and shows how we can do that. He uses return join and the fish operation, which is another way of doing composition, and talks about these things explicitly. So he's very much thinking about monads and programming with monads in the way that we do today. So this is, I think there's almost no difference between what he's writing and how Haskell's are taught to write with monads in that particular paper. Alongside all of this, you've got Richard Bird, who's thinking about the theory of lists. And so he's thinking about how can we do program calculation, program derivation from a specification? How can we reason with equations? And what do we do with this? So he works on laws and properties of programs, and he plays with those and works with those to go to actual implementations. And he writes something like this, which is a way of doing a map f over a list x plus y's, and he looks at the different properties that these have. And Spivey comes along 2 years later, sees this paper and says, hang on a minute, there are also connections to category theory here as well. So he says, well, we should really be thinking about categories not just for programming with exceptions, but also programming with lists. It's all the same stuff, the same monads apply. And so let's see, I think he says something interesting here. Many of the laws in Bird's theory of lists are precisely the conditions for various constructions to be functors, natural transformations, adjunctions, and so on. He basically says in his future work that he should be thinking about the theory of monads seems especially promising in this connection as Beck's theorem on classification of algebras, yada, yada. So he's basically saying monads are the way to not just think about exceptions, but also about non-determinism and all sorts of other things. He also implements a variation of what we'd call the free monad today, which is basically a way of turning syntax trees into a monad where binding an operation is syntax substitution. And so we see that this is where the bind symbol comes out in the programming context for the first time, at least its type does. Its name is subst in that paper, so subst is bind. That's not how monads made their way into mainstream Haskell, though. So although this theory was well established by Spivey, I don't think it was popularized, and I don't think people knew about it particularly. But Wadler did find this paper and did pick it up and realized its value. And so in 1990, he wrote this paper, Comprehending Monads, where he added the idea of monad comprehensions. So you can write some things that look like set comprehension notation, but we're talking about monads. And he, in 92, does the essence of functional programming. He has an invited talk where he talks about how we should be using monads for functional programming. And the great thing about this talk is that he has all sorts of different variations of monads and explicitly shows how each of these are useful for programming. So we've got interpretation, just as usual, the identity monad, and we've got error messages, got state, output, non-determinism, and I think this is the TARDIS monad for those of you who like strange computations that work forwards and backwards. Now, that's not quite the end of the story, because one of the troubles with monads is that they don't compose very well. And so that means that whilst you can use a monad to describe a particular effect, if you want to have more than